Today, we're tackling a question that's hotter than a lava lamp on steroids. What keeps the Earth's core hot? I mean, think about it. Our planet is over 4.5 billion years old. If it were just a big rock floating in space, it should have cooled off ages ago, right? But nope, deep inside Earth, temperatures soar to over 5,000 degrees Celsius. That's as hot as the surface of the sun. This fiery heart powers volcanoes, earthquakes, and even protects us from deadly space radiation. But how does it stay so toasty? In this video, we'll peel back the layers of our planet like an onion, explore the ancient origins of that heat, and uncover the sneaky processes keeping the fire alive. Stick around till the end. First things first, to understand the core's heat, we gotta know what Earth's made of. Imagine our planet as a giant cosmic jawbreaker. It's layered, it's colorful, and it's full of surprises. The crust is the thin, crunchy shell we live on, only about 5 to 70 kilometers thick, like the skin on an apple. Below that is the mantle, a gooey, semi-solid layer of a rock that's about 2,900 kilometers thick. It's hot, but not core hot. Temperatures here range from 500 to 4,000 degrees Celsius. Then we hit the outer core, a liquid ocean of molten iron and nickel swirling around like a massive blender. It's about 2,200 kilometers thick and hits temps around 4,000 to 5,000 degrees. Finally, the inner core, a solid ball of iron-nickel alloy, roughly the size of the moon, squeezed under insane pressure and blazing at up to 6,000 degrees Celsius. That's the hottest spot. But where did all this heat come from in the first place? Let's rewind the clock to the birth of our planet. About 4.6 billion years ago, our solar system was a chaotic dust storm, a spinning disk of gas, rocks, and ice orbiting a young sun. Gravity pulled bits together, forming planetesimals, which smashed into each other like a cosmic demolition derby. These collisions built proto-Earth, and boy were they energetic. Each impact released massive amounts of kinetic energy, turning into heat. It's like dropping a hammer on your foot. The energy from the fall becomes pain. Heat in this case. The biggest bash, a Mars-sized object called Theia, slammed into Earth, ejecting debris that formed the moon. That mega collision alone melted much of the planet into a magma ocean. So, residual heat from formation is one big source. Earth started hot and has been cooling ever since. But wait, if it's just cooling, why hasn't it frozen solid by now? Space is a giant heat sink, right? Well, that's where the plot thickens. Earth's cooling rate is super slow thanks to its size and insulation. The mantle acts like a thick blanket trapping heat inside. But that's not the whole story. There are active heat generators down there. Now enters the hero of our story, radioactive decay. Deep in Earth's mantle and core, elements like uranium, thorium, and potassium are breaking down atom by atom, releasing energy as heat. It's like having tiny nuclear reactors scattered throughout the planet. How does this work? Radioactive isotopes are unstable. They shed particles over time, turning into stable elements. This process, called decay, gives off heat. For example, uranium-238 decays over billions of years, and there's still plenty left from Earth's early days. Scientists estimate radioactive decay accounts for about half of the core's current, heat around 20 terawatts of power. That's enough to light up every bulb on Earth 1,000 times over. But why is this concentrated in the core? During formation, heavier radioactive elements sank toward the center due to gravity, a process called differentiation. It's like sorting M&Ms by color. The dense ones go to the bottom. This keeps the heat production humming along, slowing the cooling process dramatically. Without this, Earth might have cooled too fast, losing its magnetic field early on. It's crucial for life. Now for the third big player, latent heat from the inner core's solidification. Wait, freezing releases heat? Yep, it's counterintuitive. But think about water turning to ice. It releases energy as molecules lock into place. Same here. The inner core is growing slowly, about 1 millimeter per year, as the outer core cools and iron crystallizes onto it. This phase change from liquid to solid dumps latent heat back into the system, warming things up. It's like a self-sustaining cycle. Cooling causes freezing, which releases heat, which slows the cooling. Estimates say this contributes another 5 to 15% of the core's heat budget. Combined with primordial heat, about 30–40%, and radioactive decay, it's a triple threat keeping the furnace lit. Now, you might be wondering, but how do we know all this? Scientists use seismic waves from earthquakes to X-ray the interior, plus lab experiments that squeeze rocks under core-like pressures. It's not easy. We can't drill that deep. Our deepest hole is only 12 kilometers, so models and simulations fill in the gaps. Okay, so heat's being generated, but how does it move around without escaping too fast? It's convection's turn. The mantle's giant, slow-motion churn. Hot material rises from the core mantle boundary, cools near the surface, and sinks back down like boiling soup in a pot. This conveyor belt transfers heat outward, driving plate tectonics. But its inefficient Earth loses about 44 terawatts of heat to space annually, mostly through oceanic ridges and volcanoes. That's tiny compared to what's inside, so the core stays hot for billions of years. Comparing Earth to smaller planets, Mars cooled quickly because it's half our sizeless volume to hold heat, thinner blanket. Its core is mostly solid now, so no strong magnetic field. But Venus, it's a super hot surface, but its core heat dynamics are still a mystery. Earth hit the Goldilocks zone for long-term heat retention. So, is the core cooling forever? Yep, slowly. In a few billion years, it might solidify completely, shutting down the dynamo. But don't worry, we've got time. The sun will expand into a red giant first anyway. In summary, Earth's core stays hot thanks to leftover formation heat, radioactive decay, and latent heat from freezing. It's a delicate balance, keeping our world alive. If you loved this, smash that like button. It helps the algorithm spread the science love. Comment below, what's the craziest Earth fact you know? And subscribe for more. I'll see you in the next one.